So in yesterday's session, if I open the slide, I shared up to this lecture 12, which is the Macromechanics of Composite Material, third lecture. Okay. So where we were till what we have done, we look into help in psi model. Okay, longitudinal and transverse stress. And I told you that this mechanics of okay, I'll open that slide itself and we will go. Okay, so I told you that uh, there are three methods actually for calculation of our uh, mechanical properties of composite material like longitudinal Young's modulus, transverse Young's modulus, Poisson's ratio, that is measure Poisson's ratio, and in plane shear modulus, means shear modulus of your composite material. And for doing this, there are three methods are there. Mechanics of material means that is based on solid mechanics concept. Then semi-empirical formulation where we are going to use experimental data and some modeling techniques, and then approach entirely based on theory of elasticity, means whatever are the assumption of theory of elasticity, we will take the advantages from there and we will develop this thing. So there are three methods are there, and we looked and we found that the mechanics of material concept, what the it Young's modulus what you are going to get in E1 is okay. We can go ahead with this one for our design process. But the moment transverse Young's modulus and your especially these things comes, what is called as shear modulus, when it comes, then we found that there are some gap in the sense, if you see the transverse Young's modulus for one of the case of a composite material where fiber is boron and matrix is epoxy, then we found that experimentally for different volume fractions, you see there is a gap here. This is the prediction from mechanics of material approach, and these are my experimental data. So there is a large gap here. So to fix those gaps, there was one method called semi-empirical method, and there are many semi-empirical methods, means where they are going to take assistance from our experimental data itself to model the transverse shear modulus and the in-plane uh, mm, transverse Young's modulus and in-plane shear modulus. So one of the technique which is very famous in a semi-empirical relationship is Halpen-Shai model. Okay, and in Halpen-Shai, I told you that they didn't touch this longitudinal Young's modulus. They told that the Young's modulus, what you are getting, E1 value from mechanics of material is okay. There is no issue in this one. But the moment we saw that the E2 value, for E2 value, they have proposed some modification here. Okay, you see E2 they have written in terms of like this one. Okay, where the some new constants you can see it is appearing here, like zeta is there, then nu is there, or rho is there, whatever the name is you are giving, and this volume fraction of fibers. So this is okay. And this I told you that these two terms, eta and nu, they about what is this is called in Greek. This any idea?
So the first one is zeta, second one is eta, I think.
Eta is not this one. Eta is something different. I remember zeta we are writing like this, and maybe eta only it is. Okay, will so there is
Sir,
a
generally all of the efficiency or this kind of symbol looks like it's eta only,
Mm.
sir.
Okay, so there is a relationship. These eta and zeta are not independent. Okay, they are dependent on each other. So you see, eta is depending on zeta value. Okay, through this relationship. So with this, what is that Young's modulus in transverse direction you are getting? That is from the Halpin-Psi model. Okay, and when they plot it, when they have done the plotting of these things, they found that the some improvement is there. Okay, it is not that exactly it is going through the prediction from the helping size exactly going through the middle of this all this experimental data are doing a better fit? No, this was the fit what they are getting. At least some of it is going to it is lying close to some of the experimental data you can see here. Okay, so this was the so some improvement was there with the help and shy model, but that this improvement was still not very good. Why? Because I'll tell you. Okay, and yes, when we looked at the shear modulus part, okay, we found that the similar modification they have done here, okay, for getting the shear modulus of a composite material. So this is what GM is your shear modulus of your matrix material, and V is the fiber volume fraction. So now, so this was their proposal for in-plane shear modulus. But what happened? This in-plane shear modulus concept, what they have told, it had some limitations also. Like usually, what we consider circular fibers in a square matrix. Means when we looked into our volume, representative volume, or if I put the composite material directional like this one, then what we assume that there are fibers, cylindrical fibers like this one present in this matrix material. So this is three-dimensional in nature. Okay, but when I change it into two-dimensional, and then for a representative volume element, what I'll find, I will represent this as a one unit where I will have a fiber at the center and matrix material. So this is a square, this is a square boundary, and fiber is a circular. Okay, in two dimension. Okay, so usually this is the case, and they have found that for a circular fiber in a square array, zeta value is equal to 1. Okay, so if I put the value of zeta equal to 1, if I put the value of zeta is equal to 1, maybe here, if I put the value of zeta is equal to 1, zeta is equal to 1, and put the value of shear modulus for fiber and matrix here, then I will get a value of eta. And once I get the value of eta, I will put the value of eta in this position here and here. Then I will get the value of G12. So what was the issue with them? The value of zeta for a circular fiber is given, okay, results only for a fiber volume fraction up to 0.5. Means up to 0.5 fiber volume fraction, the result was acceptable. Okay, the moment that you are means if I come here, you see here up to 0.5, maybe if it is this one, then it should be 0.5 up to 0.5. Okay, the close to 0.5, the prediction from Halpen-Psi model was okay for fiber volume fraction. Okay, but the moment I get a more, if you increase the fiber volume fraction and do the experiments, you will get a large scatter of your experimental data, which is very away from my, that data is not available. Okay, but anyway, I'm just for illustration, I'm putting the experimental data are too away from my Halpen-Psi prediction. For what? In plane shear modulus. Okay, so what they have done in that case? In that case, again, these all are the research activities. Okay, so what they have done, there was one guy, Hewitt and Malherbe. Okay, they suggested some further modification. Okay, and they told that your eta value you can't take as 1 directly for my a conventional composite material where the representative volume element is a circular in a square boundary square matrix. You can't take is as directly zeta is equal to 1. You have to add few more quantity here, and that is given by this one. You see such a long, such a tedious work that guy has done. You see how much you fiber volume fraction raised to the power 10. So such that much of iterations he must have done something, and then he arrived at this expression that your zeta value you can't take it as 1. You have to use zeta value like this one. Then from zeta you have to calculate eta, and once you are calculating eta, then you are going to putting the value like this one. So this is the improvement. So this is how they have done the thing. But the result for this one, I need to search that how much improvement they were getting with Hewitt and Malherbe equation. So we saw that maybe I'll summarize here only that mechanics of material, and I have semi-empirical. Okay, mechanics of material and semi-empirical uh, yeah, approaches. So it was very easy. Okay, but the approach was good on for only E1 calculation. For E2 and G12, this was not correct. Okay, so from then we came to a semi-empirical formulation. There I told that E1 was in, they kept intact the process for calculation of E1. For E2, they have done some modification, okay, and for G1 also too, they have done some modification and some improvement was they found. But still, you can say there is gap here because I just put approach from one of the person like Halpensai, and I found that there is a gap. So, and I am just putting only one of the modifications by one of the author. If you search in the literature, you will find lot of modifications and lot of different approaches people have found developed in this semi-empirical relationship to develop semi-empirical relations in the semi-empirical domain to find the values of E2 and G12. Okay, but this was in standard books. Most of the books they will write only about the Halpensai and Hewitt and Malherbe suggestions, so that I have put here for you. Now, elasticity approach, when I was going through the content for the elasticity approach, it was very, very fundamental approach. Okay, there no ambiguity here. All the means equation of equilibrium of forces, compatibility of your strains, then Hooke's law relationship in three-dimensional dimension, all the things it takes account of all the things. That means this approach is very fundamental. Okay, energy equations, energy, then the force balance equation, all the things. So this is one of the most fundamental approach where you will not find any gap. Okay, gaps are very less, but the approach is very, very tedious. Okay, it is not that this is that much easy, because when we looked at mechanics of material approach, we found that very easily we can do the derivation, how to find E1, E2 and G12, Nu12, very, very easy. Some derivations we were able to do. And in semi-empirical formulation, we found that we didn't write the derivation part. We just wrote the expression, and we found that the expression are going to improve the bring some improvement. Okay, but in elasticity approach, even the expressions are very. It is not that much easy to either remember or do the coding for that one. So we need to put some more effort in when we are modeling the expression for E1, E2, G12, Nu12 in elasticity approach. So what is an elasticity approach? It is it's a very conventional approach only. Means you are having just wait. Okay, I had got something. Okay. Okay, so in this approach, what is there? Cylindrical fibers are assumed to be embedded in the matrix. That is how we are doing in all the cases. Okay, either it is arranged in a hexagonal pattern, or it is arranged in the regular square pattern like this one. Both the things are possible. Okay, so what is the elasticity model described here are called as composite cylinder assemblage, CCA model. Okay, So here what is there? One assume that the fibers are circular in cross section, spread in a periodic arrangement and continuous. Like this one, fibers are continuous means there is a, if I put in the 3 dimension, means fibers are continuous. Okay, so there is no breakage of the fiber. The fiber is not like this one, that there is a breakage of the fiber, or there is any slip built in the fiber, or there is any defect in the fiber, or the fiber matrix interface is intact, like this one. Okay, so the representative volume element consists of a cylinder made up of a single inner solid cylinder bonded on a outer, like this one. How the representative volume we will see. Okay, that if this is how there is a fiber. Okay, and it is surrounded by a matrix. So in previously what we were looking, our assumption was like this one. There is a fiber in a square matrix, but here the fiber is in the cylindrical matrix, like this one. So the radius of the fiber is A and the radius of the matrix is B. You see A and B is there. So if if A and B is the radius, then the fiber volume fraction I can write as pi A square into H and pi B square into H. So this will go, and Vf will be equal to A square into B square. It's a ratio of your square of radius, like this one. So how the things are done here? For the longitudinal Young's modulus E1 value, for Young E1 value, uh, you see here we are applying a force to P. Any force you are applying, and this force is applied in a such a way that it is acting on your fiber also, though I have not shown here, but it is acting on your fiber also and acting on your matrix also. Everywhere it is. So it is evenly distributed force. Okay, like this one. Okay, so the stress, so the axial stress which is coming on this entire composite material will be equal to P by pi b square. Okay, you should not take an you should not assume that the sigma 1 will be equal to P by something like pi b square minus a square. No, it's not like that. It is means B is your from here to here, the radius is there. So over all the surface your this thing is acting. Okay, so so this is the stress acting on this one. But from the Hooke's law, for a linear elastic material, because composites are linear elastic, okay, we can write sigma 1 is equal to epsilon E1 by epsilon 1. So what is E1? Is the longitudinal Young's modulus, and E1 is the axial strain in the one direction. Means this is the one direction. This is how it is assumed, two direction, and it is one direction. Okay. So what is going to, what we are doing here actually? We got the stress value, and we are getting stress value from this expression. Okay. So we are equating both the things, and I am going to get the value of E1. So E1 I am going to get like this one. So this is my longitudinal Young's modulus E1 value. But you see here still I am getting a known value, force and strain E1. So what we have to do? So this force value P and strain value in the one direction has to be expressed in the term in the known quantities. What is the known quantities? I know the Young's modulus of fiber, Young's modulus of matrix, and Young's modulus and the fiber volume fraction I know. So I have to express these things in some function of E F E M V F V M, like this way. Then then my expression will be more generic. It is not generic, because in that case you see the moment you change p value and this value will change. So I will not be able to get a generic value here. So I have to express these things in terms of known quantities which is there, because this thing has to be constant. It has to be constant. So but these force and these things are variable here, so all the things I have to change into known quantities. So hence the force applied and the axial strain has to be expressed in this time. So this is going to be a challenge for the analytical persons who are working on analytical part, means developing formulation. Okay, it was really a challenging task. And Lot of iterations has been done and a lot of assumption, theory of elasticity, then your boundary element method, then lot of things they people have applied, and then they came up for with the final expression. So that derivation part I'm not going to show you here, because when I looked into the books also, I found that it is going to take 3-4 pages, at least 2 pages it was going to take. So final expression I'm going to show you about the longitudinal Young's modulus by using theory of elasticity or elasticity approach. You can see here, this one should be like this one in terms of P and E. And when P and E1 we are expressing in terms of known quantities like EM, EF, VM, VF, I am going to get expression like this one. You don't worry that this is the final expression. This is the thing what you are going to get from theory of mechanics of material, minus you have as such a big quantity. Are you able to see this thing?
Oh, yes, sir.
Yes, sir.
So, but you have to be very wise here to understand the thing. You see here, EM, okay, I know this thing. I know this is fiber volume fraction, okay, but these are volume of fiber and volume of matrix, not fiber volume fraction. Are you getting? Small v.
Yes, sir. It is dimension. It has units.
Yeah. So this is your volume of fiber alone, not fiber volume fraction. Okay. Then again, if I come to the denominator, I have this quantity. This is volume of matrix, and this is fiber volume fraction. This is volume matrix. This is volume matrix, and you here see here. Here you have again volume of fiber like this one. What is the volume of fiber you are going to put. So this volume of fiber will definitely depend on the radius and the height of fiber, radius and height of fiber. Then your volume of matrix definitely will depend on the diameter of fiber, volume of fiber, and your height. And in fact, this will depend on A also, because the situation is like this. I have a fiber at the center and this one. So if I assume that the volume of fiber matrix, that will be equal to pi mm, b square minus a square into h. Correct or not? It will be like this one. So you see that much expression is there. So that this part maybe we will see whether we can include in our assignment or not. Okay. So this is how the longitudinal Young's modulus in one direction is
So
calculated.
shouldn't it be divided by 4?
Which one?
The the VM which you have written here. Pi by 4 times b squared minus d squared.
Yeah, into h.
Yes, sir.
Huh. Where is you want to put 12?
So like B and C would refer to the. Oh, never mind, sir. Fine. Never mind.
No,
It's fine.
no, no. It's fine only.
It's
It's
fine,
a
sir.
circle, area of circle into height. That is what
Understood, sir.
volume,
Understood, sir.
we tell volume. Na? So that's what I'm telling you. If you come here, VM is a function of A also, not only B and H. That's what I wanted to tell you here. And the major Poisson's ratio, you see here, this is what you are getting from mechanics of material, this much. Okay, and this is this a big quantity you have to add here. So derivation wise means I found that these are very tedious. Okay, if I show you the books also, you can find that in fact in lot of books these things is not given. Okay, but in one of the book it is given. So there you find that such a big expressions are there, and we have to use these things. So longitudinal shear strength and major Poisson's ratio, two things are there. Okay, and these two things I need to still maybe what thing is there, transversal Young's modulus and in plane shear modulus. Transversal, so this should be E2. Okay, so what we have seen till now, we look till now E1, G1, 2. This we looked at. So these two things, E2 and new one too. From elasticity approach, I need to tell to you. So maybe we will drop the call today. Okay, just, and I will share these things tomorrow. We will discuss these things with you tomorrow. Is that fine?
Yes, sir.
Because I was going through a lot of literature. Okay, it's not that from one literature we can get all the things, and I want to have all the steps with you. Okay, so I have shared all the things here. You see here up to lecture number 12, all the things, video and everything is there. Okay, so you can have a look on these things. So again, so these two things are there. Then the stress components are there. So maybe 2 more days we have to meet. Okay, we will meet again tomorrow for just maybe around 8:50 after the dinner. We will again connect. Okay, and we will discuss the thing. Is that fine?
Yeah, yes, sir. It's fine with me.
Okay, I don't have much things, so I don't want to waste time also here, because again, once I drop the call, then again I will start collecting the information and we'll meet tomorrow in that case. Okay. So in that case, what we'll do, Sunday we will discuss the code,
Okay, sir.
how you are solving those three problems. You need to explain to us that how you have solved the things. So Sunday will be your work. You half time, you can take half an hour for your all of you. You have to show it to me how you are doing the thing. Okay, maybe I will no, no, this is not an evaluative part, but I definitely this will show you that how much you are putting effort for this paper. Correct.
Okay, sir.
Okay, it's not that you have submitted assignment, then the grading is done like that. No, some interactive work should be there, one by one to one work like this. Okay, both the ways it should go. So we will meet in that case Sunday also. But tomorrow we are meeting to finish this part. Okay. Okay. I'll drop the call in that case. I'll stop the recording.
Thank you, sir.
Okay. Fine.
Thank you so